Think about how many times a day you tap, swipe, and pinch your phone screen. We do it hundreds of times without even thinking. It just works. It feels like magic, right? But have you ever actually stopped and wondered what is going on under that perfectly smooth sheet of glass?
I mean, really think about it. There are no buttons, no moving parts. It's a solid object. So how in the world does it know, down to the exact pixel, precisely where your finger is?
Okay, so first things first, let's bust the biggest myth right now. Most people assume you're activating the screen with pressure, that you're pushing on it, but that's not it at all. The real secret, the thing that makes this entire dance work, is electricity.
And that leads us to what we can call the touchscreen illusion. See, we think we're having this physical interaction, but the screen is actually sensing something else entirely.
And here's the crucial part. Your phone screen doesn't feel you. It can't. What it's actually doing is sensing a tiny electrical change caused by your body. The moment you touch it, you literally become part of the circuit.
So, this is where you become the key to the whole operation. This entire amazing system relies on a basic property of every single one of us.
Turns out, your body is a pretty good conductor of electricity. I mean, not like a copper wire, but because we're mostly made of water filled with dissolved salts, we're basically walking bags of salt water. We can carry an electrical charge. And that is exactly what a modern touchscreen is designed to look for.
This brings us to the core scientific principle here, capacitance. Now that sounds like a complicated word, but the idea is simple. It's just the ability to hold onto a small electric charge. Think of it like a tiny, tiny battery. Well, your phone screen is covered in a grid of these little batteries, and in a way, so are you.
So how does the screen actually use this idea? Well, it's not just a blank slate of glass. It's engineered with this hidden, totally invisible structure.
Let's break it down. On top of the main glass, there's an incredibly thin, totally transparent coating of a material called indium tin oxide. The important thing about this stuff is that it's conductive, and it's etched into this microscopic grid of crisscrossing lines. The phone's controller is constantly feeding a tiny, stable electrical charge into this grid. So when you're not touching it, there's this perfectly balanced electrical field across the entire surface. Every one of those little intersections is just sitting there, holding its charge, waiting.
And that's where the real action begins. Because when your finger gets close, you don't add anything to the screen, you actually take something away.
This is the perfect way to think about it. Your finger acts like a sink. Because your body can also hold a charge, when you get near the screen's stable field, you disrupt it. You pull a tiny amount of charge from that grid into your finger. You are literally stealing charge.
Now this little theft of charge, as tiny as it is, causes a measurable drop in capacitance right at that exact intersection on the grid. And the screen's brain, the controller, is watching every single one of those points, all the time, just waiting for that little dip. And when I say it's watching, I mean it is unbelievably fast. The controller scans that entire grid more than 200 times every single second. That's why it feels instantaneous. The system detects the change before your own brain has even fully processed the feeling of your finger hitting the glass. So that explains a simple tap. But we do so much more than just tap, right? How does this same system handle all the complex gestures we use every day?
Yeah, what about pinch to zoom? How does the system handle two fingers at once without getting totally confused?
It's actually brilliantly simple. The controller is so fast and precise that it just sees two separate sinks, two different drops in charge at the exact same time. It tracks the X and Y coordinates of both points independently. Then the software layer kicks in and interprets the changing distance between those 2 points as a pinch or a spread gesture.
Now, this same principle also explains a very common frustration. Why can you use your finger but not a regular glove or even your fingernail?
Well, the answer goes right back to that core concept. Things like fabric, plastic, or the keratin in your nails, they're all insulators. They can't conduct electricity, which means they can't act as a charge sink. When you touch the screen with a glove on, you can't steal any charge. So as far as the screen's electrical grid is concerned, absolutely nothing happened.
And this really shows you why the technology we use today, capacitive touch, completely took over. Older screens, called resistive screens, think old ATMs, worked on actual pressure. You could use anything to poke them because you were just physically pushing two layers together. But they weren't very precise, and they definitely couldn't do multi-touch. Capacitive screens are just faster, more accurate, and way more versatile.
So, when you peel it all back, that magical feeling is revealed to be just a breathtaking piece of engineering. It's a constant, high-speed conversation between an invisible electrical grid and the natural conductivity of your own body.
Kind of makes you wonder, doesn't it? What other everyday magic is actually just incredible science, hiding right under our fingertips? Let us know what we should break down in our next explainer.